So thank you very much for coming to listen to this. This is a very ambitious talk. I have a huge amount of content to get through, so I'll do it quite quickly. But it's the thing I'm currently most excited by, so I thought I would try and present it. So this is work I've done mostly with my co-author, Lucia Vidicamo, and there's a picture of us winning the first ever CSAT Best Paper Award. Okay, so there's the outline of the talk. I'll quickly talk about the context motivation. The talk is actually about dimensionality reduction, so probably most people are familiar with that already. But I'll go through some context because I'm using some examples later in the talk. And unfortunately, there's a fair amount of background, but okay. So why do we want dimensionality reduction? And also, this mechanism gives dimensionality reduction for non-Euclidean spaces as well as Euclidean spaces, which is one of its major novelties. So this context we're probably all very familiar with. The idea is that we have a large collection of objects that we want to search. So we take the large collection, we pre-process into some feature extraction, some representation, typically a vector of numbers. And then when we want to find similar objects, images or otherwise, we take the individual query object, do the same feature extraction, and then use some distance function over this large database. And of course, we have some lovely results, especially nowadays using neural networks, but we have the problem of the efficiency and the size of these representations. Okay. So you may well, this is becoming a well-established technique. So there are lots of deep learning convolutional networks that are actually designed to classify images, but it turns out we can pull layers from the middle of these networks and apply distances to these representations. So use them as semantic representations for the images. So I can't point. So this is a beautiful picture, which I didn't draw, of the AlexNet network. The point is that on the left, you put in an image, and on the far right, where it says class probabilities, you can determine whether that image is typically, a dog or an elephant. This is what AlexNet does. But if you look to where it says the fully connected layers, the far left of these, layer 6, we call this the FC6, that's a vector of 4,096 numbers. And if you apply, for example, Euclidean distance over those vectors, then you get a very good approximate function for image similarity, for some real conceptual image similarity. So this works very, very well. For those of us old enough to have worked with things like the MPEG-7 descriptors, none of which worked at all, the results of this are quite stunning. They look like this. So this is a collection of 1 million images. It's the MeaFlickr. It's a public image retrieval collection. And these on the left are literally 5 random images from the collection. And to the right are the most similar, where most similar means the smallest Euclidean distance to these FC6 descriptors. So this is almost like magic. Some people understand how it works, but it's a very, very good functional proxy for actual similarity search over images. So it's very, very good. And the problem then remains the size and number of these descriptors. So these descriptors are 4,096 floating point numbers, which is about 16K per image. And even if you're only searching 1 million, because nowadays we think of 1 million as a very small number, in fact 1 million is a very big number, it's almost infeasible to search the images using these representations. They're high dimensionality and they're large, and this is an old-fashioned network, by the way. GoogleNet has 200,000 dimensions in the equivalent layer. So we need to do something with these representations to try and make them more tractable. And there's a second aspect to this that I'm very interested in. Almost everybody uses a very simple in fact, a ReLU'd L2 normalized Euclidean distance, which is actually a cosine distance, over these representations. Now, partly there's a reason for that, because to some extent the network was trained using this distance, but also it's just a fast available distance, and Euclidean distance, of course, has got literally hundreds of years of research on way to manage Euclidean distances. And particular dimensionality reduction is very well understood in Euclidean spaces. But here's my belief, which is not provable at the moment. Here's a distance that somehow should work much better over these descriptors. So the individual vector components range from some negative number to some positive number in a fairly tight range. So we could apply a sigmoid function to these to make them all positive. Then we can coerce these vectors into probability vectors, and then we could apply something like Jensen Channel distance, which has a sound information theoretic basis for distance. And probably this is a better way of comparing almost any data, actually, which comes out of these sort of networks. Probably. I say probably, it's almost impossible to prove this for various reasons, but it does not help by the fact that this distance metric is about 2,000 times slower than Euclidean distance. So you're really talking then about running a query for maybe 10 days over 1 million objects, which is it's quite hard to get statistical information. Okay, so that's sum up that's the context. We have these image search problems, which are increasingly becoming common and important over these large vector spaces, and we absolutely require to make these representations smaller as best we can. And personally, not many people are interested in this. I also want to use much more expensive metrics over these spaces, which makes things even harder. So dimensionality reduction mostly only exists for Euclidean spaces, mostly. Okay, so you probably all know what this is. There's a number of very well-known techniques for improving the speed, or in fact for reducing the size of the representation. So this is completely generic, not just to do with images and neural networks. With maintaining as far as possible the meaning of the distance relation over the objects. So for example, principal component analysis, typically people learn as an undergraduate. Multidimensional scaling, which is very different, usually ends up with exactly the same results, interestingly, over Euclidean spaces. But this is supposed to be a topological rather than linear method. And random projection, which in many spaces works as well. So a very quick overview of these things. And where I'm heading to, within 5 minutes if I can, is a new technique which I've written is better than any of these. So that's a really major claim, because these are old, tried, tested, heavily researched. And better, I'm going to claim, gives you a better quality of reduction. So some of these techniques are aimed at speed rather than quality. You can never have both. But as importantly, it works for spaces such as the Jensen Channel space. In fact, it can reduce a Jensen Channel space to a smaller space for which Euclidean distance then becomes the metric. So that was actually the motivation for this. I never expected this to work better for Euclidean spaces than these other techniques, but it kind of does. So that's where the excitement is. So very briefly, one quick slide on each. I say you probably all know all of these things already. This is the classic Wikipedia picture of how principal component analysis works. If your data happens to be inside its many dimensions in some sort of interesting flying source or ellipse shape, then we can compress the number of dimensions because there's redundancy in it. So in this example, here's a two-dimensional collection of data, which can be clearly compressed by essentially squashing it down the longer dimension. So, for example, if we're reducing this FC6 space from 4096 to 200 dimensions, That sounds like a lot, but actually there's a lot of redundancy in the 4096 dimensions, so this is not bad. We produce a coefficient array using standard PCA algorithm, and we multiply the data by the first 200 columns of that array, and we end up with, we move from the 4096 dimensional data to 200 dimensional data, and the distances, the corresponding distances in the 200 dimensions are, as best as possible, preserved with respect to the original space. Multidimensional scaling is conceptually very, very different, tends to converge on exactly the same answers for various reasons, which are complex mathematically. But with multidimensional scaling, the input is the set of all distances within the original set, and the output is a Euclidean space of the number of dimensions you tell it, which minimizes the stress over the pairwise distances. So it is doing something fundamentally quite different from PCA. It's preserving the pairwise distances with respect to each other as best as possible. And the problem is, as I said, the input is the all pairwise distances within the set. So if you've got 1 million data sets, you've got 10 to the 12 pairwise distances. There's ways around that. You can make it scale better only for Euclidean spaces, but it's still an order of n to the 4. So people like Edgar cringe when you say n to the 4. It's not going to be helpful. And finally, random projection, and this just sounds stupid, because random projection, you basically construct a random orthogonal matrix and multiply the same way as you do with PCA. But the Johnson-Lindenstrauss theorem actually predicts there's a surprisingly small error for doing that. And it turns out that lots of times when people are using PCA, all they're really doing is doing a random projection, because there's no real difference in the component variance in the original space. And quite often, this particular form of random projection it's not truly orthogonal, but it's got lots of zeros, so in theory it's much faster to do the matrix multiplication. So these are probably the 3 main methods that are used, and let's move on to the novel method. But the interesting question, and this is almost a research issue, is okay, so in a minute we're going to have 4 different mechanisms for doing dimensionality reduction. How do you tell which one's best? Well, there are still people writing research papers on how to compare different dimensionality reductions, but there's a fairly standard toolbox which is generally known and accepted. The answer is it depends why you want to do it, which is the better technique, of course. But this is visually very attractive. This thing left and right, they're called the Shepherd diagrams, which is just the x-axis is the distance in the reduced space, and the y-axis is the distance in the original space, and that's a scatter plot of some pairs of objects in the original space. And essentially, if in a perfect mechanism, these points will all lie up the y equals x line, which is the dotted line there. It really doesn't matter for most purposes actually where they lie. What you want is a nice thin spread going up the has to be monotonic increasing. So on the left-hand side, you can see that looks like a much better mechanism than the right-hand side, because you've got this nice thin spread. We can actually measure the spread by using a measurement called Kruskal stress, and the black line, the solid black line, is the best fit isotonic relation between the distances. So it's constrained to being always increasing, and then it minimizes the horizontal distances between the points. And then you can measure that. So the Kruskal stress on the left is 0.026, and on the right it's 0.059. So you can both see how good it is. And it's also very useful to have that number, which more or less represents the appearance of this chart, because then you can plot that number over different reduction dimensions and see how the quality decreases as you reduce the dimensions you're reducing to. Okay, so I'll show you lots of these charts in a bit. But first, I'm going to try and explain to you in about 20 minutes what's really probably rather a complex mechanism. So please ask questions when I go too fast. Okay. So this is our contribution. We've actually been working this for about 5 years now, not with this goal in mind, but it's quite a lot of new results. It works for Euclidean spaces. It also works for some quite significant classes of non-Euclidean spaces, which is, I say, where we started from. And I'm going to talk about this concept of Hilbert embeddability, which is quite complex, I think. In my view, I'm not a geometer, but it doesn't matter. Okay, so you don't need to be scared of this because I'm not going to try and explain really what it means, but it has an important property that we're going to use. So as with everything, there are some nice Wikipedia articles about these things. The important point is that we're going to use the topological geometry rather than a linear function, so matrix multiplication. We were not going to use matrix multiplication. What we're going to do is like take the original space, we're going to randomly sample points in it and use that information to try and do the reduction. Rather than looking at the whole space, we're looking at the shape of the internal space somehow. Very hard to explain. But we're only going to use distances. The same as multiple dimensional scaling, we're only going to use distances as input. We're not going to look at the coordinates. This is why we use Hilbert space, because Hilbert spaces are essentially Euclidean spaces that don't have coordinate systems. I think Edgar might be angry with me for making that statement. It's not what a mathematician would say, so therefore I'm not a mathematician. Okay. But you can think of them safely as Euclidean spaces that don't have coordinates. So we're just going to use distances. And for example, the point here is we just, so cosine distance, Jensen Channel, and any quadratic form distance is a triangular distance, and possibly we can convert other non-Hilbert spaces into Hilbert spaces by some transformations, such as taking the square root of the distance. So the single asterisk at cosine means, well, you have to have exactly the right definition of cosine before it's a Hilbert embeddable space. And the double asterisk after the fact we can always map, for example, by square rooting the distances, is a statement that may not be true. It's true to some extent, but I'm not sure how true it is. So input welcome on that one. Okay, so the only thing I'm trying to explain the important properties of Hilbert spaces here. So metric spaces are fairly well understood. They have all these properties. And I've highlighted the triangle inequality property, which distinguishes many sort of dissimilarity measures from proper distances. Triangle inequality, so for any three objects in a space, essentially the longest distance, so there are three objects, three distances, and the longest distance is less than the sum of the two shorter distances. So that's how the metric properties are usually stated. So I'm saying that only because what I want to introduce is the notion of a finite embedding. So here's an equivalent property. For any three objects in a metric space, it's possible to construct a triangle in two-dimensional Euclidean space, where the vertices of the triangle correspond to the objects, and the edge lengths of the triangle correspond to the distances between the objects in the original space. So another thing a mathematician wouldn't say, it's obvious that these are the same properties. But Lucia, who is a mathematician, spent at least a day shouting at me because I said these were obviously the same until she'd proved that they are the same to her satisfaction. So these are the same property. The important thing is, though, we're looking at a fairly abstract property in the metric space and looking at a very concrete property in the Euclidean space. And the underlying concept is that every metric space has a finite 3 embedding, which means that any three values can be embedded in a Euclidean space in the form of a triangle. And that's the property that a Hilbert space allows you to extend. So this is now true of only Hilbert spaces, not generic metric spaces. is you can embed any n objects in an n-1 dimensional Euclidean space. So any 3 objects, you can form a triangle. Any 4 objects, you can form a tetrahedron. Any 5 objects, you can form a 4-dimensional simplex. And I don't think there's any cool word for that in geometry, like tesseract and globe and so on. There should be a word for this, but there isn't. And so for any, the general concept is a simplex. A simplex is a geometric structure which is a finite number of points, all of which are connected to all of the others by edges, and which exists in an n-1 dimensional Euclidean space. So the Hilbert spaces have this property. I can take 20 objects from a Hilbert space, I can calculate all the distances in the Hilbert space, and I can construct a simplex in 19 dimensions with all the edges are preserved. So I have a guaranteed right to be able to construct this structure in the Euclidean space. So here's a lovely mapping from any Hilbert space, which, by the way, includes all Euclidean spaces, but also all these other spaces. I can pull them into a Euclidean space for a finite number of objects only, is what I'm guaranteed. Do ask questions. So we use this ability then to define the transform from the whole space into the Euclidean space. Okay. So we're first of all going to choose a relatively small set of objects from the Hilbert space. We're going to take the relatively small set of k objects, and we're going to construct a simplex in k-1 Euclidean dimensions. And we have an algorithm for doing that. I don't know if that was obvious or not. I had to invent it because I couldn't find it on Wikipedia, which obviously is my go-to for solving this sort of problem. So we've got the k points, we've constructed the k-1 dimensional simplex, and then for every other value in the original space, we can create a k-dimensional simplex by calculating the distance from that value to all the elements of R, the k elements of R, and finding then a unique point in the in the k-dimensional Euclidean space, which is the k-1 dimensional simplex used as a base. So think of a triangle as the easiest base, and you're forming a new apex. This is easy in 3 dimensions. So I've got a picture. So this then maps every object in the Hilbert space into a single coordinate in the k-dimensional Euclidean space. So yeah, this is the easy example. Mapping is into a 2D space. This is one of these examples where you can think fairly safely in 2 and 3D spaces, and everything works up in the higher dimensions that you can't possibly visualize. Okay. So this is true for any Hilbert space. We can select 2 objects from the space. We can construct a line, which is a 1-dimensional simplex in Euclidean space. We'll map one of them to the origin, and we'll map one of them to the x-axis at the correct distance between these 2 points. And then for all other objects in this space, we calculate these 2 distances, and there's a unique point above the axis where this lies. So we're then converting the whole of the set into a 2-dimensional coordinate system. And it looks like this. Okay, on the left-hand side. So this simplex we've constructed, or the simplex, the mapping formed by the simplex, we're calling sigma. So we've got along that x-axis on the left-hand diagram, there's sigma of the first reference point and sigma of the second reference point. That's the simplex base we formed from these 2 things. And then we've got 2 other U0 and U1 objects from the space. And now it's clear, I think, that there's a unique point that these map to in the 2-dimensional space, such that the last coordinate is positive. So there are always 2 points these can map to, but always going to pick the one where the last coordinate is positive. So it's above it's actually above the hyperplane which contains the simplex. So that gives you the altitude of the apex of this. Okay. So, okay, we can do that, hopefully I've established, but why do we want to do that? Well, we want to do that because you can probably see in the right-hand picture, the right-hand picture is kind of showing a three-dimensional space. So this is where it becomes slightly tricky. We also know, because we have the Hilbert properties, we could form a simplex in a higher dimension. So we're mapping our points in this example into 2D space, but we know that there also exists a tetrahedron where all of the distances are preserved perfectly. So where is the, if we've mapped these points, where is the correct position for U1 such that the tetrahedron can be formed, not just the two triangles? So we're also using the distance between U0 and U1, and it's somewhere on that circle. So I usually try and bring a prop, which is, it doesn't matter. So you can imagine folding and unfolding these two triangles around the axis, essentially. So the true position, if we plotted the tetrahedron from these 4 points, is on that circle. And therefore, as we're only looking at the two-dimensional projection, we only require the three-dimensional projection to exist, and we know that the distance on the left-hand picture then is the lower bound of the true distance in the original space. Okay. So the true distance in the original space, you can see on the right-hand picture, is anywhere between sigma of U0 and that circle. And so the smallest possible distance is when these are both projected into the 2D space. The biggest possible distance is if we negate the last coordinate of U1, so that's an upper bound. And the true distance is anywhere on that circle. Okay, but it must be between these two bounds. So this is quite cool already. We're taking, in high dimensions, we can take some horrendous space with no easy properties. We're mapping it into an n-dimensional Euclidean space to say, trust me, this extends to any number of coordinates in any dimensions. And we have a cheap lower bound calculation. So the lower bound in the original space is the Euclidean distance in the projected space of the n dimensions you get from the n reference points. So we can do better than that, but I'll have to take you back to high-dimensional Euclidean spaces. And I'm talking about Euclidean spaces now, but these properties probably hold for, well, definitely hold for all Hilbert spaces as well, because they're almost Euclidean spaces. And we're going to think about the distribution of angles. So many people may have come across this before, many people may not have done. It's almost well known that in a high-dimensional vector space, the angle between any two randomly selected vectors is likely to be close to 90 degrees. It's not that well known. It's well known probably in people that have done fairly advanced maths at university. Anyway, so let's look at this. This is really important. The distribution of angles is not uniform in a high-dimensional space. This is one of those examples where you absolutely cannot use your 2- and 3-dimensional intuition in the geometry because it completely changes in higher dimensions. So we're looking at this diagram in the top right, and we're going to pick 2 points from any Euclidean space, and we're going to consider a locus of a third point C, where the distance from B to C is fixed. Okay, so in 2 dimensions, we pick 2 arbitrary points, and we're looking at the circle around C. Of course, in many dimensions, we're looking at the hypersphere centered on C. And what we want to know is the distribution of that angle theta when we pick many examples of C. And obviously the mean of this angle is going to be 90 degrees, probably obvious. But the important point is the way that this distribution happens. And that looks, when you look at that picture in 2D, it's going to be a uniform distribution all the way around between 0 and pi. Okay. But it's not. So the distribution is actually very similar to this function sine to the n of theta, where n is the number of dimensions. So what we have is, again, I need a spherical prop. You're looking, if you think of your high-dimensional Euclidean space as being an orange or a football, you're looking at it from there, and it turns out all of the uniformly distributed points are around a circle, which is around the top of the sphere that you're looking at. And the reason for this is the formula for the volume of a hypersphere, where that thing's rotated around the x-axis. And the point is, if we go straight to that, okay, these are the probability density functions on the right-hand side as the dimension increases. So indeed, for a 10-dimensional space, you have that dotted blue line, you have a fairly even probability distribution. But once you go to 1,000 dimensions, almost every one of these angles is very, very close to 90 degrees. So why does that matter? It matters because this is the same picture I drew before, but from a different perspective. So you can see these 2 points, each of them projected into a 2-dimensional space, which is the grey plane along there. And now imagine a viewpoint on this, which is the V in the right-hand picture, and you're looking at the distribution of the uniformly distributed space around that circle, which is actually a hypersphere. And almost all of these points in higher dimensions, because all of these distances are from the domain space, not the Euclidean space we're mapping into, almost all of these points are very close to 90 degrees if it's a very high-dimensional space. And we can easily formalize this. The formula at the bottom is the true distance, okay? So not in the projection. This is the true distance between D0 and D1 in the original space. And you can see the right-hand term is, okay, the important thing here, the 3 terms before the last term only rely on information that's available in the 2-dimensional, the lower dimensional space. And the last term is a term which is a factor of cos theta, where theta is that viewpoint angle. And so if theta is 90 degrees, that term disappears. So we can make an estimate of this space by blanking out that last term. Okay. This is the theory. We have a good estimate of the true distance, which we can calculate from the projected space in Euclidean space by essentially this formula, which is very like Euclidean distance, only we're adding the last 2 terms together instead of subtracting them and squaring them, essentially. So that's it. I try to describe the nSimplex relation, which maps the Hilbert space UD into a k-dimensional Euclidean space. And then this distance, actually, take my word for it, or I can show you a paper. The Zen distance is the square root of the Euclidean distance plus 2xk yk, where that's the last coordinate in the space. So we have a very simple function over the k-dimensional Euclidean space we mapped into, which will give us, we believe, a very good estimate of distance. So that's why this suddenly becomes a dimensionality reduction, because we're mapping from perhaps a high-dimensional Euclidean space into a much lower-dimensional Euclidean space, and we've got a cheap function, which is not the same as the Euclidean distance, which should give us a good estimator if the domain space is high-dimensional. And we can also use it for non-Euclidean spaces. So this is how well it works. And it works very well, like really very well. These are, on the top row, these are the same diagrams I showed you earlier. So the Shepherd diagrams with the critical stress measurement added. But now the left-hand one is using this Zen function of the nSimplex mapping. Middle one is PCA, and the right-hand one is random projection. And I only haven't plotted multidimensional scaling because it's almost always exactly the same as PCA. It gives you the same quality for all of these measures. And you can see that you get a much nicer, tighter line for Zen, much nicer, it's a bit nicer, than you have for PCA, and they're both better than random projection. The critical stress is half. So this is measured over a series, so there's only about 50 data points in the scatter diagram. The critical stress is a real measurement with some statistical validity. It's about half for nSimplex Zen than it is for PCA. And this is over real serious data that people really want to query. Remember, this is a 4,096 dimensional data set, which has really good image semantics in the real world. So yeah, we've got a much better, truer representation of distance when we reduce to the same number of dimensions. I haven't said this is reduced to 109 dimensions, which is the PCA gives you about 80% accuracy. So 80% of the variance is contained within the most significant 109 dimensions of this set. And okay, so we repeated this for actually, I think 8 different data sets in the paper we are currently writing. And this is true across the board. The bottom row is Twitter Glove. These are word representations that come from Twitter. These give you a really interesting semantics over the meaning of words. I don't know if you come across it. And again, we've got the critical stress using Zen is less than half of the critical stress using PCA. And again, much better than random projection. So it works pretty well. And these charts now are showing critical stress and Spearman row. So these are, again, standard displays of how well these are working. So on the x-axis now, we have the number of dimensions that we're reducing to. So on the left-hand side, this is reduction from, again, so the bottom row here is FC6 from AlexNet. So this is the 4,096 dimensional data. We're reducing it to between 200 and 2 dimensions. Okay? And the plots on the bottom left chart are the critical stress. And you can see that the nSimplex Zen stays almost at 1. It's almost perfect, all the way down to maybe 40, 30 dimensions. Whereas PCA starts to degrade fairly steadily from about 100 dimensions downwards. And by the time you get down to 5 dimensions, we've still got really quite respectable stress scores from Zen. 5 dimensions, can we reduce 4,096 dimensions to 5? That seems absolutely impossible. And the reason is because it's a fairly high dimensional space, and we're using this 90-degree angle thing, which works fairly well in this space. Twitter Glove, the results are even better, even though it's a low dimensional space, so there's lots of things we don't understand yet. But yeah, essentially, the solid black line is the Zen. It's better than the others almost always across the dimensions, but the most spectacular results are when you get to very low dimensions. So the far right-hand point in the top left diagram, genuinely, that's a 2-dimensional reduction. So we're reducing 200 dimensions to 2 dimensions and maintaining the ordering, essentially, of these observations. The right-hand chart's a Spearman row, which is another way of measuring the topological orderings. So we're not looking at the absolute distances. We're looking at the relative distances within the space, which is what's important. And in fact, Zen also does very well with absolute distances. And here are some results from non-Euclidean spaces. This is, again, representations taken from Mirflicker. This is using GIST, which is one of these rather more old-fashioned image representations. But the reason I'm using this data set, we've seen in the past that using Jensen Channel distance over the GIST representations is actually the best way for looking for near-duplicate images, which is an important sub-problem. So again, this is reducing GIST from 480 dimensions down to 100 dimensions in the top row. And so the left-hand side is Zen, the right-hand side is a technique called landmark multidimensional scaling, which is similar to multidimensional scaling. You can use it for non-Euclidean spaces, and it's horrendously expensive, actually. It's very, very time-consuming to calculate. But again, the critical stress for Zen is half what the landmark MDS is. And across all the different dimensions on the bottom row, see that, again, as the dimensions get small for critical stress, there's a relative better performance for this Zen. So, is everything really that good? Well, not quite. There's one outstanding problem, which is that this mechanism is less good for very small distances. And this is unfortunate because very small distances might be what you're most interested in if you've got a very large data set. And there are things we don't understand in here. So this measure is, again, we're reducing, this is mere flicker, the FC6 from 4,000 down to between 1,000 and 2 dimensions. And we're measuring recall, which is a complex measurement. But essentially, this is how well are you, so the ground truth here is the whole data set's 1 million objects, and we're looking to extract the 1,000 most similar ones. And this measure is some combination of how well this nearest 1,000 matches the ground truth. And so you can see in the left-hand diagram, everything's pretty good, other than random projection, through to about 500 dimensions. And then the Zen gets worse sooner than PCA and MDS. In the right-hand case, the Zen is much better. This is a different metric over the same data, in actual fact. This is probably a better metric over the same data. Zen's much better down to 300 dimensions, and then, again, PCA and MDS are worse. So we sort of understand why that is, but we haven't tried to do anything about it yet. So I'm putting this slide in, just to be honest, this is not always better for everything, but it is almost always better for everything. So as I was producing these experimental results, there were over 8 different data sets, and drawing the lines, I kept surprising me how well this was doing. So that's me finished. I'm sorry I've packed a huge amount, I believe, into that talk. The paper I'm trying to write about this is already about 40 pages long, so it's probably ambitious for a talk, but hopefully you followed. If you're interested and want to know more, then of course I can give you things to read about this. But the conclusions are really exciting. We've definitely found a new dimension in actually reduction technique. It's almost always better than all of the well-known established techniques. That's a pretty good result. For Euclidean spaces, also you can apply it to many non-Euclidean spaces, and essentially it's always better and always essentially than landmark, which is the only other technique I know of for non-Euclidean spaces. Again, being honest, the cost comparisons, it's much cheaper than PCA and MDS to actually construct the transform, because it only analyzes a tiny number of reference points, whereas they analyze the entire space, if they possibly can, in quite a costly operation. But the mapping from objects to the space is about an order of magnitude slower. But I'm running that using MATLAB on an M1 Mac, where all of the matrix operations are hugely optimized using techniques that are hundreds of years old in analysis. I don't think there's an inherent reason why this mapping's slower. I think it's just not optimized the way that matrix multiplication is. And yeah, there's still some interesting questions in here. I think it might be possible to make this better for the very small distances as well. But I'm not quite sure how. Thank you. That's me done. Happy to take questions or observations or knowledge. Thank you.
Okay. So, question. For PCA, we have the Carnot theorem that gives you even some distortion, predefined distortion. You can find the minimum number of dimensions to embed the thing using the Carnot theorem. So in this case, what will be, if any intuition of given some distortion, what will be the minimum dimension you can embed this thing?
Okay, thank you for the question. As they say in US Airlines, thank you for the question. Have a nice day. I've absolutely no idea. There's lots of really. This is really, as far as we are, is observing these sort of fairly standard tests, yeah, that I don't know much at all about refining this to other situations, including in those last tests when we're testing Jensen Channel distance with no idea even what might be a suitable number of dimensions other than just trying them and see what they look like. So again, for Euclidean space, you can use PCA to see a sensible embedding size based on the variance capture, but so yeah, don't know much about how to do anything other than the technique itself. But if you've any ideas, I'd be very grateful.
There is another question. ¿Alguna otra pregunta? Puede ser en español. I have a question. I have been working linear. With linear projection dimensional reduction, and it's not it's a different kind of dimensional reduction. So the first question is about, did you compare with this kind of techniques, non-dimensional reductions?
Other than multidimensional scaling, which is
non-linear,
sort of topological. Well, that kind of is non-linear in a way, depending on how you apply it. Yeah. Other than that, no, I haven't. Yeah. But
because the idea in this kind of techniques is to capture the meaning, the semantic of the KNN graph.
Yes.
And this is not exactly the same. Well.
Yeah. No, I understand the question.
Yeah.
But still the answer is no.
Okay.
But it's a very interesting thing to
do.
You're absolutely right. Because as I said, I think the reason this works well is because it's doing the random selection of objects from the real space. And so it might be similar in the analysis in terms of the extrapolation from the shape of the manifold, which is clearly not one amenable to PCA. There was some other complex manifold in there.
It's really interesting the kind of complexity that you are explaining, you are reporting, because the other the other techniques are more costly.
Yes.
Perhaps in the best ones are similar to PCA, but you are reporting smaller complexities than. Yeah, I understand well. Because you are using just a few points.
The construction of the mapping is much cheaper. Yes.
And if you
but the application of the mapping is more expensive.
Okay. Well, that's a part of my.
But interestingly, so for the landmark MDS, you have to do a large number of distance calculations for each point you transpose. Whereas in nSimplex, you only have to do one per dimension of the target space, which is much better.
Yeah.
But
well, it sounds pretty interesting, and maybe we can talk later.
Yeah.
Thank you. Don't know if there is another question.
Yeah. The thing that for indexing, you actually want the smallest distances. If you fix beforehand some points, I mean, if for example, if in 2 dimensions, if you start with the one single triangle, okay, and then you know that for any 3 points. You can embed it correctly in the plane. So you start with a triangle, then take this the smallest triangle you can find in the set, right? No. This is a suggestion.
This is what I could do. Okay. Yes, okay.
You start with the smallest triangle you can find in the set, and then add other points to the nearest edges and continue from there. Yes. So you will have a minimum distortion 2-dimensional embedding, although very expensive because you need to find the things. Okay, but you can approximate that. So do you think that that could be one way of obtaining a minimum distortion mapping for a fixed number of points?
No.
Okay.
Because I've tried that. I've tried, so everything, all the examples I showed, and all the examples in the paper are literally using random selection, because I've tried many techniques for finding a better selection of pivots, and none of them, in general, none of them is better. For projection to very small dimensions, yes, some of these tactics work. But in general, they don't. And I think it's, so I don't really understand why this works as well as it does, but I think it's to do with sort of capturing the essence of the manifold that the space is sitting in. So random is almost always best, if that's true. But yeah, you're quite right. I have tried, taking very small distances to construct a tiny little simplex. In fact, what happens then is you get very high apexes. Mm-hmm. And the height of the apex is definitely one of the problems with the very small distances, because the lower bound, so this is not a metric space, by the way, that we're mapping into. It's highly non-metric. So the distance from an object to itself is essentially the height of the apex where that object maps. So I think that's why we have a problem with the very low dimensional, the very small distances, is there's noise in the heights of the apexes of the whole space. If you're mapping a lot of points in, then the near neighbors are being drowned by things that happen to be low apex values. So maybe there's something we do about that. But before you ask, taking a huge simplex or the biggest also doesn't work. I don't know why not. But yeah, I suspect there is a way of constructing the simplex carefully, depending on the context of what you want to do. But yeah, I don't know much about that. Everything I've tried has failed, I can tell you.
I have a final question. I have a question, and it's more about... I have a question. It's about the traditional visualization techniques. Mm-hmm. Most of them are just kind of PCA or others that project to two-dimensional, just to see, or three-dimensional spaces. Have you used this approach to produce this kind of maps, visualization, and use traditional measures like, maybe the NIST database, the digits, and see what happens with this, if they cluster or not?
In fact, you can't. Because the mapping is not to a Euclidean space, you can't draw the two-dimensional diagram.
Okay. Yes.
However, you can take the mapping to the low-dimensional space, and you can use multidimensional scaling to push it into a two-dimensional space, which I have tried doing, and I have no conclusive results from that. But yes, it's a possibility.
Okay. Well, thank you, Professor Richard, for being here.